so the guy, and so the guy, he was like, well, there is a flat universe theory where the world is moving at an acceleration, right? So he calculated the acceleration equation at 9.1 meters per second. He was like, in order to get the mind frame to that speed.
You guys get a sketch looking something like this green thing up here?
Yeah.
Does that look green to you guys? I'm from an angle. I can't tell. It looks black. All right, well, it is what it is. So let's see. When t equals 0, cosine of 0 is 1, right? So I could say that, you know, if I want to throw this thing on a coordinate system, and if I do what I did last time and I say this is x and this is y and this is z, who was it that told me that in their engineering they have x and y swapped? Yeah. So you have x over here and y over here.
So yeah, our machines,
Yeah.
Z is like the control head.
Yeah.
And the x coordinate moves the table this way.
Yes.
And the y coordinate moves it towards you.
So positive y is towards you.
Positive y is towards you. Yes.
So the only thing I can think about that will be really screwed up by that is if you ever have a cross product computation.
Okay.
Because we have something called a right-hand rule that tells me the cross product points up as I go rotating x to y. But for you, that would point it down, which is interesting. But other than that, I think you're fine. Yeah, that's interesting. I mean, we have to adapt our axes to solve problems, right? And it just makes more sense for the workers, so they do it that way, right? And, you know, x is right and left. They've known that for years, right? And so y is going to be this. And you guys are going to see a lot of Calc 3. We're going to solve applications, and we're going to put the axes kind of where we want them, okay? And so in particular, if you have something that's a helix shape, could it be a spring? Could it be DNA? There's a lot of different, well, anyways. Whatever it is, right, we're going to try and exploit the symmetry by putting the z, that's a horrible drawing of what I just did, but I'm trying to put the z right up the center, right? Okay. So, anyways, it says find the parametric equations of the line tangent to the curve when t equals pi, right? So if I'm right here at t equals 0, well, by the time I get up to t equals pi, I'm going to say that's around right here. The reason I'm saying that is because I'm seeing 180 degrees that I've kind of gone around the circle, right? Like if I just look for a moment at the xy plane, and if I say, actually, t equals 0 would be more here, right? On the x-axis, right? So if that's the point 1, 0, 0, then I guess pi is not here. T equals pi is on the other side, somewhere around here. The vertical z distance at that point is pi, and that's what I'm indicating right here. So that's the point P that we're talking about. And what I'm picturing on the xy plane is I've done this. But now I've also gone vertically up in the air towards me, pi. Okay, so we want to go ahead and find this tangent line at point P. I guess it might look something like this to me. It just touches. It has to have some kind of a vertical slant, right? Because we want this thing to be rising. Because what we're learning today is when you take the derivative of position, you get what? Velocity. Remember that? How many remember this idea of velocity being the derivative of position? What about the derivative of velocity? What does that give me? Okay. So those ideas from Calc 1 come back today. It's just that we're going to put them in higher dimensional settings. And if you have that down, that's kind of the take-home today. So we're going to take a look at this line and try to find its parametric equations. And so, like I told you guys, I have this point. All I really need is the direction of the line. I need the direction vector. But the direction vector you can get by thinking about this vector here, the velocity vector. And that velocity vector, I'll call it v, right? So v of t is equal to r prime of t. And we learned last time that, well, how do you take derivatives of vector-valued functions? You just go component by component. So you guys did negative sine of t, cosine of t. And then what's the derivative of t? Well, it's 1, right? So if I write them with this bracket notation, I guess maybe that's a little bit nicer sometimes than the IJK notation. Right? Okay, so if I want to know, so this is a function that can give me any velocity vector anywhere on the curve. This one. But what I'm noticing is that the z component of the velocity vector is always 1. And that means that this thing is always rising at a constant elevator rate, I guess. So if we take the pi and plug it in, I have r prime of pi is negative sine of pi, cosine pi, 1. And so I'm getting, what's the sine of pi? 0. Cosine of pi, and then positive 1. Okay? So that's the vector. 0, negative 1, positive 1. Really nice answer, I think. And so that's my v. And so when they say find the parametric equations of the line, we did this last time. We did it. So I guess I've already used r, so maybe I'll use s. S of t equals S initial plus V initial t is one way to write this. And so what I'll say is maybe I'll do it this way. Okay. X of t, y of t, z of t is one way to write my vector S of t, because it's a three-dimensional vector, is equal to, oh, this is not good. I just realized something I did. I went to my linear algebra notation that I use for their class. You guys are like, what's he doing here? Sorry about that. What I was trying to do is write something like this. X of t, y of t, z of t, that's the vector S, is equal to S initial, well that's my point P, so we could say negative 1, 0, pi, plus t times, and then the direction vector is 0, negative 1, 1. And maybe this should be parentheses because it's a point, and this should be brackets because it's my direction vector. I think I like that. And so now, again, if I say what are the parametric equations, one of them would be negative 1, well, plus 0t, right? So x of t is negative 1. Y of t is, let's see, y of t is, well, 0 plus, or actually be minus, because there's a negative 1 there, so minus t. And z of t equals what? Pi plus t, right? So there's the three equations. And so I'm saying that the equation of this line is given by this set of equations. And now let's think about that for a minute. When I say x is negative 1, that means that this line, I don't care where you are on the line, the x value is negative 1. Can I see that from the picture? Well, point P, remember, we got by going 180 degrees, right? So we were over here. So if you think about what the line of tangency looks like. Again, I'm looking straight down on the, if I look straight down on the helix, what shape is it? It's a circle because I don't see any of the z change, right? And so if you think about that velocity vector, if I look straight down, it looks like this. Now we know there's a slant. I can see it in the three-dimensional picture. You guys with me? So that makes sense now. X is -1. Should the y be -t? You know, that's an old linear equation where the slope is -1, right? And you can kind of see that. And here the z-slope is +1. So that I think it makes some sense. I think it's a worthwhile exercise to do. Okay. Questions on 2? Number 3. What did I ask you guys to do? Find r of t. So what do you have to do? Antiderivative. So this is just like a calculus review, right? How do you take the antiderivative? Well, see, r of t is going to be the antiderivative of r prime of t dt, right? And so, well, okay, that's a Calc 1 equation. Now it's a Calc 3 equation, right? Isn't that cool? And the nice thing is that that goes component-wise also. Antiderivatives go component-wise just like derivatives. So what I have here, let's see, I have this equals, so what's the antiderivative of 1 over 1 plus t squared dt? That's what the coefficient of I is, right? Plus the antiderivative of, well, this next one I'm going to write as t to the -2 dt, and then that's the component of j. But the next one I'm not going to write as t to the -1 because 1 over t is special, right? So here's your integration review. You could argue that these are the 3 most important integrals. You could argue that. Nah, you can't argue that. Yeah, you could. I don't know.
T to the -2.
Do you remember? Yeah, t to the -2 we can do? What's that? Let's see. It's t to the -1st, but then you need a negative there, right? Bing, bing. Okay, that worked. How about 1 over t? Why didn't I write that as t to the -1? Because you try the same trick, and it doesn't work, does it? You just have to kind of remember this one. What's this one? The natural log of... Do you remember this? Why do I need absolute value?
Plus TK.
Always positive.
Yeah, why?
The natural log never goes past 0.
Right, the natural log is not even defined for negative numbers or for 0, right? So this will only work if t is greater, well, if t is not equal to 0, right? But actually, look at the original function. The original function is not even defined if t is 0. So there's some nice things happening there. How about this one? It is. It's the arctangent of t. There's a whole trig substitution thing you guys did in Calc 2. You guys did some amazing things in Calc 2. But I'm not going to do that. I'm just going to say we know that. Okay. And then, do you remember this one? Plus c? Well, wait a minute. What do I mean plus c at this point? I think what I really mean is plus c. Right? Because this is a vector-valued function. Right? So you don't just add a number to a vector. That doesn't work. Now, what do I mean by this? A constant vector? Well, actually, we have an example of one on the previous problem. Remember, we computed, let me go back up there. We computed r prime of t, and we got this expression. Then we plugged in pi, right? And we got a vector, and that vector was this black direction vector. Are you guys with me on this idea? Now, what happens if you take the derivative of a constant vector? Well, you would take the derivative of the components. But what's the derivative of any one of these constants? So the derivative of a constant vector is 0, 0, 0, which is a vector. It's the 0 vector, it's called. That's a little bit weird at times, I think, okay? But I just want to kind of, I feel like I better mention those things in the, right away when we're doing the example. So now, I'd like to know what that constant is. And I can compute it because of this fact right here. Okay? We were given that that R of 1 is equal to 2I, and what is I again? It's 1, 0, 0, right? We were given that. So let me write that down. We know that, well, 2 times 1, 0, 0 is 2, 0, 0 is equal to, and let me go ahead and use this notation. And what I'll do for this vector C is I'll call it, how about I call it Cx, Cy, Cz. Those are constants. Now when I do this, these are numbers, Cx, Cy, and Cz. They're each constants, right? And what I have here now, let's see. I need to plug in what for t? 1. Does this make sense to you guys? So what is, maybe I'll just write it down because I think arctangent of 1. And then here, this is negative, well, 1 over 1, because t to the negative 1 means 1 over. So yeah, there's some notation problems here because I didn't write my I, J, and K here. So maybe I should have done it here, comma, comma, without the pluses. I think that would be a little bit better notation. Okay. Sorry about that. And then here I have the natural log of 1. Okay. So we're able to solve at this point, I think. We have 2, 0, 0 is equal to, what's the arctangent of 1? That's an angle, right? Anytime I see an inverse trig function, I think over on the side, I think, okay, theta is the arctangent of 1, and that means the tangent of theta is equal to 1, right? Do you guys know what theta would be there? Pi over 4, right? 45 degrees is when the sine and you can think sine of theta over cosine theta equals 1. So sine of theta has to equal cosine theta, and you're right, it's pi over 4. Okay, so that was a long-winded way to say 2, 0, 0 is equal to pi over 4, comma, negative 1, comma, and what's the natural log of 1? 0. Plus, again, these constants, right? So now you can get what these things are from solving, right? You could subtract. And so my final answer to this problem, okay, I had R of t was this plus c, but my final answer, I guess I have just enough room on the group work. Wow. So let's do that. The final answer will be R of t equals, and so I guess I could write arctan of t, right, plus what? What is that constant? It would be 2 minus pi over 4 when you solve for it. So I'll say plus 2 minus pi over 4, and that's right. So there's the x component. The y component would be, let's see, negative 1 over t, and then what is cy? Plus 1 when you solve for it, okay? And then the z component would be, well, cz is 0, so it's just going to be the natural log of the absolute value of t. There is my answer to group work number 2. Any questions on this morning's group work problem? Yes?
I just got one.
Sure.
Where'd you get the 1, 0, 0 when you did R
of 1 equals 2 times the 1.
It was r of 1 is equal to 2 times I. This is a bold-faced I.
Okay.
I is the vector 1, 0, 0.
Okay.
So that's what that means.
Thank you.
Sure. Anything else? Wow, time flies when you're having fun. 10:55. I think I'm going to throw you guys at your 10-minute break now. We'll come back at 11:05 and we will go over a few homework problems and also have a little bit more about acceleration and velocity. Okay? We'll do that. Here's a problem for you. A particle moves along a curve in space let's say at a constant speed. Now, is that easy to do? Well, I guess we see that modeled sometimes, right? Well, or do we? So if my, if I roll a ball and just watch it roll and I don't kick it again, right? Is that moving at a constant speed? Why not? Okay, so you have friction, right? So then I take a rocket and I shoot it into outer space to reduce friction once it's up there, right? Or the moon. Is the moon moving at a constant speed?
It's falling towards the Earth, so I think it's accelerating.
I didn't ask if there was acceleration. I asked, is it moving at a constant speed, or does it speed up and slow down?
Its orbit is perfectly circular, it would be moving at a constant speed.
There's some nice discussion going on here, right? Matter of fact, when I roll that ball, if you have a nice round and you have a speedometer and you are next, you might say, yeah, that's going at a constant speed for a while, right? If there's really low friction, right? So some of it is how precisely can we measure, right? But then some of it is, there's this theory going on too. So, but this is a theoretical question. If you had something moving along a curve, so I guess that's different than my ball. The moon example may be a little closer, right? That's a particular curve. Is the orbit a circle? The first time I ever learned about the word ellipse, I was in 2nd grade. I didn't have any equation of an ellipse, but I learned that the planets make elliptical orbits. And I knew that for years, and then I was, where the heck was I? Case? Yeah, someone asked me to lead a seminar for teachers that were coming in on, the solar system and Mars and we the planets and all this. And so one of the things we did was we modeled the orbits, and I realized, oh my gosh, these things aren't ellipses. I mean, they are. But if I draw that's the orbit of the Earth. It's a very close to a circle ellipse for all of the, there were 2 exceptions. Mercury had quite a bit of eccentricity. It looked like an ellipse. And Pluto, but that's not even a planet anymore. They knocked, said, you're out of here, right? But the rest of them, if you looked and hold it up to a kid, what shape? Circle. Don't start telling me it's an ellipse. The eccentricity is like 0.00 something. I mean, and you have to be 1 to be, or close to 1 to be very oblong. So, okay, back to our program. Oh, show that its velocity and acceleration vectors are always perpendicular. I think this is a good exercise. show that its velocity and acceleration vectors are always perpendicular if you have it moving at a constant speed. So, well, what do we do? Well, I guess let's use our given information, right? How do we represent constant speed? What is speed? The magnitude of velocity. That's a nice definition. Velocity and speed are different because one of them is a vector and one of them is a scalar, right? Speed is a scalar. It's the magnitude of velocity. And so when I say that we have a constant speed, I guess what I'm going to start my argument with is this. If the magnitude of velocity, so, how am I going to write that? I'll write it as absolute value of a vector is equal to a constant. I'll use a lowercase k for my constant. Right? Oh, and let me do something here. Let me do this. Let me suppose that that constant is greater than 0. Why? Well, if it equals 0, if the speed is 0, yeah, it's not, I mean, the real exciting particle, right? Okay, so let's not worry about that case. Let's suppose that k is greater than 0. So we have some speed, and who knows what kind of curve, it's moving along. I don't know. But if we have that, then we can write, well, how do you compute the magnitude of a vector? The length of the vector, right? I mean, the picture is you have this, right? How do you compute its length? Well, yeah, I remember in physics class we did square root because there's a distance formula going on, right? And so the same is true even in 3 space, right? So if you have it in 3 space now, maybe my picture looks like this. And so I'm like that, I'm like that, I'm like that. And so, okay, come down here, and then you could compute that vector, I guess, by doing perpendicular Pythagorean theorem, right? Let's go back to the 2 case. This is too hard for me, okay? So how do I compute this distance? This distance, right, the magnitude of v in this case would be the square root of what? I agree. X squared plus y squared. I like that. And then the magnitude here is the square root of x squared plus y squared plus z squared. I mentioned this last time, haven't proved it. Great exercise. And then there's a better way to do it. It's to write this. Another way of expressing the speed would be the square root of v dot v. Does that make sense to you guys? I mean, look at this vector v. In that picture there, v is equal to the vector xy, right? And when you dot a vector with another vector, what is xy dot xy? It is. How do you do dot product? Remind me. Oh, I'll remind you. Or even in this example, when you do xyz dot xyz. First thing, does dot product give me a vector or a scalar? Gives me a scalar. That's one of the reasons it's useful here. This equals, so I mean the general formula, x1, y1, z1 plus x2, y2, z, or dot x2, y2, z2 is equal to the scalar x1, x2 plus y1, y2 plus z1, z2. So there is my definition of dot product, right? So that's why when you guys tell me it's x squared plus y squared, Do you see how that's the same as the square root of xy dot xy? Does that make sense now? Okay, because you would, right, x1, x2 would be x squared, y1, y2 would be y squared. I'd like to take advantage of the fact that we've learned about the dot product in Calc 2, and those of you that haven't, I appreciate all the catch-up you guys are doing. That's really good. Okay? But there's a reason I picked this problem out today, too. I said, oh, we can get to do some dot product. So then what happens? Well, then I want to square both sides, right? If I square both sides, I get that v dot v is equal to well, k squared. That's another constant, by the way, right? Now, what I'm trying to do is I'm trying to show that the velocity vector and the acceleration vectors are always perpendicular, okay? And there was a fact we learned about dot product also. Sometimes the dot product can tell you that the vectors are perpendicular. As a matter of fact, as an example, in R3, can you tell me what I dot j would be? Well, because it's 1, 0, 0 dot 0, 1, 0. So yeah, that's 0 plus 0 plus 0 is 0. You guys with me on that? Okay. So dot product 0 is equivalent, as it turns out, to the vectors being perpendicular. By the way, just as a reminder, if you do I dot I, of course, what would that be? That's 1, right? So unit vectors, right? You could tell they're unit vectors when you dot them with themselves, you get 1. Well, it's the same as what I'm doing here, really. All right, so anyways, we have this fact, but I want to get acceleration involved. And so now, since I want to get acceleration involved, now it's time to do what? Take d dt of both sides. All right? Tell you what, I'll do the right-hand side. Thanks, Paul. That was really nice of you. I know that the derivative of a constant is 0. Now the left-hand side, actually I mentioned this last time at the end of class, that if you want to take the derivative of a product, we have a product rule, right? So how does it work? Remember the old u prime v plus uv prime, right? So let me do that, the u prime v part of this. What's the derivative of velocity? You guys okay if I just call it a instead of v prime? Okay. So this would be a dot v plus what? V dot A, yeah. Are those the same? A dot V and V dot A? Yes, they are. Okay, that's important to know. Actually, you could see it, right? If I did the other way around, I would still get 0. That's pretty clear. The reason I bring that up is because we also learned in Calc 2, in theory, something called a cross product. I cross j. Let's do that. I cross j. Now, when you do a cross product, you get a new vector, okay? So the way I teach cross product is using determinant of a... Do you guys do it that way? Let me show everybody so that we're all on board. It's going to be the determinant of this 3 by 3 matrix. And what you do is you take I and you put it right there. So here's my 1, 0, 0, right? And you take j and you put it down there. So that's 0, 1, 0. And then up in the upper row, do you remember what you write? I, j, k. Okay, so some of you have seen this. Again, it's Calc 2, but it's so important I want to just clear it up today. So, okay, the way that... And then when you do determinant of a 3 by 3 matrix, I know there's shortcuts, but what I'm going to do is I'm going to expand across the top row. So it's going to equal I, the vector I, times the determinant of this submatrix right here, which is 0, 0, 1, 0. And then you might remember that you have to alternate signs. Minus j times the determinant of what matrix, by the way? 1, 0, and then what? Yeah, because you just kind of skip the column that J is in. And then it would be plus vector K times the determinant of what matrix? So let's see, if I cross out the column K's in, it would be this submatrix right here, right? It would be 1, 0, 0, 1, right? This okay for you guys? Now, let's continue. Oh, so it's not okay, because I can't. There we go. Sorry about that. All right. So let me kind of finish the calculation here. We're going to do I cross J. What do I get? Well, what's the determinant of that first matrix? 0 minus, but careful here, you got to do 1 times 0, right? So 0 minus 0 is? So that's 0. So it's 0. What about the next piece? Yeah, because you have 1 times 0, so that's 0. Ah, there we get something, right? So the K coordinate is 1 minus 0 is 1. So this proves that I cross J is equal to what? Is equal to K. There's the right-hand rule somebody mentioned today. If I do, in the X direction and the Y direction, and then I wrap my fingers from X to Y, then it points straight up. That's why Z is pointed this way for us. Okay, I cross J does equal K. But I will point out another fun fact. J cross I does not equal K. That's right. It equals negative K. So I think that's important to understand. And you can prove it. Actually, you may be able to see it. Because if you reversed the roles of these things and think about what the matrix would now look like for K, you'd have the 1s over here. So it'd be 0 minus 1. That's where you get the negative K. All right. Cross product has nothing to do with the problem I was working on, does it? What am I doing? I'm trying to review. All right, so back to the problem I'm working on. We did a product rule with dot product. And since A dot V and V dot A are the same, are you guys okay if I write this? 2A dot V is equal to 0? Right? I'll just add them together. I have one AV and another AV, so I have 2 AV. And now I'm going to divide both sides by 2 and say A dot V equals 0. And therefore, A and V are perpendicular. Isn't that a cool proof? I have a question. Where did I use the dimension of the space that we're working in, right, of these vectors? Where did I use that? Is that a trick question? Because the answer is nowhere, right? Does this work for 2 space? Yeah. Does it work for 3 space? I never said how big these vectors were, right? Does it work for 4-dimensional or 5-dimensional or 100-dimensional vectors? And the answer is yes. We won't do any of the 5 and above in this class. You want to do that, stop by 10 a.m. tomorrow. Linear algebra is all about higher dimensional vectors. And we try to do things where the vectors, the dimension doesn't matter so much when possible. This is a nice problem, right? A and V are always perpendicular regardless of what dimensional space you're working in. If what? If the motion is constant speed. Now, like I said, that's hard to have. Actually, we had an example today. We had a helix. And the motion was constant speed. That might be worth looking at one more time. Right? Because if you think about the motion here, cosine and sine, I know what that looks like. I have this periodic behavior of cosine and periodic behavior of sine. And t is kind of constantly going upward. So it's kind of like I put these three motions together. There's the component functions. And when I put it all together, I get this, right? And we computed a velocity vector already, right? I guess we didn't compute here was a velocity vector. What we didn't compute was the acceleration. If you don't mind, I want to do that now. So what would the acceleration be? R double prime of t would equal what? Yeah, the derivative of negative sine is negative cosine of t, and then negative sine of t, and then 0, yeah. So now what I want to do is I want to dot those, right? So let me do that. So back here, from the group work, problem 1, if I dot, I guess it would be r prime of t dot r double prime of t. Well, let's see. So we have, it was, r prime was negative sine of t cosine of t 1 dot negative cosine of t negative sine of t 0. What do I get? I get positive sine of t cosine of t when I multiply those two together, plus negative sine of t cosine of t, plus 0, right? So that's 0. Okay, so this was an example of a curve that you might not have thought of where we have a constant speed happening as I move up the helix. I think Cedar Point should consult us and make a new ride. That's what I think. No, they want acceleration. All right, never mind. So let's see. Next thing I wanted to do in terms of velocity and acceleration and all these, I wanted to do that baseball example I mentioned earlier. And let me get your book up here. So, yeah, I mean, there's a lot of ways to go here. The book talks about three-dimensional motion. Oh, I should mention, a lot of you have looked at this already. And then a lot of you haven't because you were like, wow, he's all this homework already and you're getting used to how this all works. Someone asked me kind of, what is it that I'd like you to do coming into class in terms of preparing for the class? All I really want is that you looked at the quick check exercises before class, if possible. So for, Wednesday, when we meet next time, what are we covering? We're going to talk about, we talk about motion in space today. We're going to talk about lengths of curves, all right? So you figure you probably have 3 hours of homework, well, 2 to 3 hours. I gave you 16 problems tonight, 5 to 80 by 5, right? But you also have, hopefully, to do the quick checks from 13.8 in advance, because that kind of then can guide where the lesson goes. Like I said, there's more for me to do in class than I possibly can if I want to do it right. So that's kind of all I'm asking as far as that goes. The way the grading works on the homework, each assignment's worth 2 points. If you got a 2, you have full credit already. But I also give out a plus. That's also worth 2 points. But that's saying you're done with this. I think you're ready for the exam for that particular section. Okay. If you get a 1, obviously you can always turn homework back in. If you got a homework with a 2 on it, resubmit it with whatever work you do later. Okay. And this is kind of the way we kind of communicate throughout the few weeks that we have together before an exam. All right. So yeah, back to the baseball problem is what I was thinking I would do based on what you guys had today. Where's that? Well, it's down here in the exercises. I think it's number 50. It's one of your homework problems tonight. So let's see what we can do here. Oh, they have 70 too. Well, golf. My son's playing a lot of golf. Here we go, 50. A baseball is hit 3 feet above home plate with an initial velocity of 60, 80, 80. The spin produces a horizontal acceleration of 10 feet per second squared in the eastward direction. All right, so let's see what we're going to do here. You're going to see me, it says find the velocity and the position vectors, make a sketch, determine the time of flight, and determine the maximum height. Let's see if I can start some of this, and we'll see how much we do, because I also want to get to some of those homework exercises you had. I got to watch my time. But I think sometimes just helping you guys get started is a great move. We will see here. One thing that would help is if I can get this window a little smaller so you can see what's going on. There we go. Okay. So, we have part B is I want to sketch the trajectory, so maybe I'll kind of get ready for that here. Okay, this is problem 50 from tonight's homework from section 13.7. And so, you know, like I said, we want to put our axes, well, wherever we want, okay? I think I'm going to have the baseball, when the contact is made, I think I'm going to call this initial point here 0, 0, 3. Okay? So I'm picturing right now, I'm in the right field mezzanine of Progressive Field. You guys know what I'm talking about? They're nice seats. Anyways, but I'm looking, and there's the contact, right? And some of you that have no idea what I just said, that's fine. All right, so then it says that the initial velocity, in a sense, right, is right here. I'm drawing a vector, and I'm trying to say that that is 30, 30, 80. Okay? That's the, I would say, initial velocity vector.
Which one are you doing? 49 or 50?
50. Yeah, actually, let me cover up 49. That could be confusing. Thank you. Yeah, I'm trying to do 50. So 30, 30, 80. Oh, that didn't help. Okay. So I'm picturing that if I were to look at the shadow of the ball, it's coming straight back above the pitcher, right? So I'm picturing it's coming straight to center field because, you know, it's 30 in the X direction, 30 in the Y direction, and then 80, so it's higher in the Z direction. Does this make sense to you guys?
Yeah.
It's a pop-up. Yeah. But they gave me another piece of information. They say that there's spin on the ball, and this is a real phenomenon. When a pop-up is hit in the infield, there's a couple rules that baseball players have. First of all, the pitcher is not supposed to catch the ball in general. Why? Well, for one thing, he's in a really awkward position after he pitches. On 1 foot, try to get back to 2. And he's on a mound, right? Or just coming off of it. And he's not necessarily an athlete. He just has a big arm, right? That's the other thing. I'm not going to diss my pitchers anymore. But no, an infielder is supposed to take it. But if you're a catcher and you get this pop-up, one phenomenon that you have to beware is that there's a lot of spin on the ball. And so you want to actually not be right underneath it. You want to back away from it so you can judge it better and so it doesn't spin and then end up over your head, which is interesting. Okay? So they say that because of the spin, horizontal acceleration of the ball is 5 feet per second squared in the northward direction. All right. Weird thing about that is they didn't tell me what's north. I guess it doesn't matter too much. Let's assume, for the time being, that, how about we say that the acceleration vector, I guess I'm going to say that y is north, and then we'll see how that compares to the answer in the back if we need to adjust it. Okay? So the spin on the baseball, horizontal 5 feet per second squared in the northward direction. So, you know, when I'm doing the components of the acceleration, I can definitely put a 0 here, right? Oh, come back to that. Come back to that. Hold on a second. And I can put a 5 here, and I can put a 0 here, plus, I want to show one more thing, 0, 0, and I'm going to say negative 32. So there's acceleration on the ball due to the spin, plus there's acceleration on the ball due to what? Okay. And so if I ask any of you what's the acceleration due to gravity, you probably say 9.8, and then I say no, this is feet, and so it's 32 feet per second. Okay. So there we are. So I guess my acceleration vector, right, is that. All right, so here we go. A is equal to 0, 5, negative 32. Of course, that is, you know, v prime of t, right? And so I could say, well, what do I know about v of t? Well, I could integrate. V of t is equal to, well, this is kind of interesting because how do you integrate these constants? You're just going to get t's when you integrate, right? Negative 32t, right? 0 times t is still 0, so I'll just write a 0 there. Plus, well, I get another vector here, okay? And you might understand that this is my initial velocity, right? Because if I plugged in t equals 0, what I want the velocity vector to be is that 30, 30, 80. You guys with me? So let's throw that in there too. It's kind of like what I did earlier, but I'm just going to save a step or two and just throw it in. Okay? So we're about to finish up and say what's happening to the ball, and let's sketch it. So again, find the velocity and position vectors for t greater than or equal to 0. Make a sketch of the trajectory. Here we go. So I have the velocity, but I know that the velocity, of course, is the derivative of the position vector. So if I want, so this is, I guess I'll write it as a single vector again. So it's going to be 30, it's going to be 5t plus 30, and it's going to be negative 32t plus 80. It's okay? So now I want r of t, so I'm going to integrate again. What do I get? I get 30t, yeah? I get, well, let's see, this is t squared over 2, so I could say it's 2.5 t squared plus, and then when I integrate the 30, I have 30t, right? Plus, or comma, and then I have over here, when I integrate, I'm going to get negative 16t squared plus 80t, yes? Plus what? What was the initial position? Yeah, 0, 0, 3. So really, I guess I could just throw a plus 3 here in the last coordinate. And I would say this is a good initial value, or I'm sorry, this is a good representation of the position function. Okay, so you see linear, quadratic, quadratic going on here as well. That's okay? So they ask a couple other questions. And I guess what I want to go to is how would we answer the other questions? Make a sketch of the trajectory. Well, that's a good question there. I almost feel like solving these other problems will help with that. And I also need to figure out, software-wise, what's my best recommendation for you. I mean, I have MATLAB software, which does a great job with that. Wolfram Alpha is not bad. I was about to plug it in there. But I want to give you a good recommendation, and I have 10 minutes left, so that may come on Blackboard tonight in the form of an announcement. Determine the time of flight and the range of the object. So this is kind of cool, because the way we set this up, when we say determine the time of flight, right, it's in the air for a while, yeah, and then it's going to come down. Will it come down right on the same line that it took off at?
No.
No, because there's spin pushing it this way, right? So it's going to end up more to left field, right? Must have been a left-handed batter. Got under it. Okay, so it's going to end up over here somewhere. I don't know where. But how do we figure out when that happens? Well, my suggestion is just think about the single coordinate z, right? So for part C, when does it hit the ground?
Z equals 0.
Yeah, it sounds to me like set this equal to 0, right? Quadratic formula. And then how far did it go? Well, now you can use your x and your y. You may need a Pythagorean theorem there. I think this is a manageable problem at this point. Let's see the last thing they ask. Where'd it go? Here. Oh, the maximum height of the object. Now that's interesting. Again, I think the thing to understand is the only thing we care about for part D, okay? So part D, again, use the z coordinate only, right? X and Y don't really affect. This is kind of one of the main ideas behind physics problems, is that you can break into components and just analyze component by component. And part of the reason that works is because derivatives work component by component. And that's really what's going on, is that you're taking derivatives of position to get velocity and of velocity to get acceleration. Okay? So here comes last night's homework number 25. And so it says R of t is equal to t2 and then 2 over t. And they say t has to be greater than or equal to 1 here. Okay. So they want me to find the unit tangent vector. Well, to find a tangent vector, by the way, I wrote it like this because I'm about to take a derivative, right, to catch up to where you guys were. You guys get 1, 0, and then negative 2 t to the negative second. Is that what you got? Yay or nay?
Yay.
R prime of t, right? So that's a vector, and it would be tangent to the path of this curve. If you have some curve here, I don't know, this R prime would always give me, well, we know if we think of this as a position curve, then that's the velocity vector, okay, which is really kind of nice. So the question is, how long is the velocity vector? And the answer is, it depends how fast the thing's moving, right? Because the length of the velocity vector is the speed. So if it's moving slowly at this particular point, you'd have a smaller vector. Well, sometimes what we want is the velocity vector. There's lots of possible tangent vectors. Sometimes in this course, we're going to want the velocity vector that indicates the thing is moving at unit speed. We want the curve parametrized by unit speed. And if that doesn't make sense yet, let me say one thing. Here, guys, what does this vector represent? Cosine t, sine t, 0. That's a circle. Very good. The unit circle, actually. How about this one? Cosine of 10t, sine of 10t, 0. That's a circle also. But normally, to get halfway around the circle, I have to go pi. I did that today in the helix example. But if I had this equation, you might say, this parametrization, I could plug in t equals pi over 10. And in other words, I would get around the circle a lot more quickly. Does that make sense to you guys? So you can think of these as the same curve with different speeds or different parametrizations. Well, that's what I'm about to do here. I'm going to give you another tangent vector that has unit speed. And so basically, the idea is this. We know that r prime of t, the magnitude you get by taking the square root of, well, 1 squared plus 0 squared plus, I guess this would be 4t to the negative fourth, right? And so that's what r prime is. And so what I would argue is that one way to get the unit tangent vector, which I'm going to call capital T of t for now, that I can get by taking r prime of t and dividing it by its length, right? If it has a length of 4 and I divide by 4, it'll have a length of 1. Really, I guess what it is 1 over the length of r prime of t times r prime of t. Because that way, the nice thing about this notation is that this is a scalar and this is a vector. And so what you see now is I'm scaling, however long this vector was, I'm multiplying it by 1 over something. And so I would argue that the answer you want is 1 over the square root of 1 plus 4 over t to the fourth, right, times the vector 1, 0, negative 2 over t squared. Although as I look at this, probably back of the book, good old Bob didn't write this. Am I right? He probably, first of all, multiplied the top and bottom by t squared.
Yeah.
Because then what happens, so you get t squared in the top. And another way to write t squared, of course, is the square root of t to the fourth times the square root of 1 plus 4 over t to the fourth, right? Do you see what's going to happen when I distribute? Running out of room here. Is this the final answer they had? I'll write it over here. Was it t squared over the square root of t to the fourth plus 4, or 4 plus t to the fourth, something like that? Times, that's what I would do. 1, 0, and then negative 2 over t cubed. Is that what you had? Do you see how they got it? I think that was worth doing. And I'm at 11:50, and I did not touch 33 today. Wow, what is that one? Oh, derivative rules. Is there a hint I can give? Yes. The hint is, you know which rule you need? The chain rule. That's the hint. Thanks a lot, Paul. The other hint is use the bracket notation. Don't use I's, J's, and K's for a problem like this. But out of time, guys. We'll can it. And hey, nice work today. That was fun. Okay, here I am working OT for you guys today. We're 1 hour and 4 minutes into this. The class is over, and I'm back in the office. I talked to some of the other instructors because I want to add to our web links something for you guys to be able to graph 3D quite easily. I like Desmos for two-dimensional graphs. They don't have much for 3D. Wolfram Alpha is okay, but if you want the full functionality that they've had for years, I mean, I used to always go to them. You either have to pay
or you use one of these widgets. So I found a parametric curve plotter widget. Thought about putting that on. But what I think I want to go with for you guys is GeoGebra. I don't know if you're familiar with this, but I bet some of you are. More and more high schools are using this free software as an aid for their math classroom. And it does some pretty nice 3D graphing. You'll notice here we have a helix plotted, kind of like we had today. Actually, it is the one we had today. Cosine, sine, and t are the three functions. So this is the format that you use for GeoGebra. On the other hand, there's other things you can do. So you can introduce what are called sliders. And so what I just did is I just clicked on a second curve, which I'm calling B rather than A. As a matter of fact, I'm going to turn off A. Let's not look at that right now. Let's look just at B and see what it does. So what we did here is we put R as a variable, C as a variable, and then T also, the end time is what it says. And so we're going to plot from 0 to end time rather than from 0 to 2 pi like we did before. And what this allows is this allows me to plot more of the curve or less of the curve that could be traced if you went infinitely. If I want to get the same curve I had before, I can make R equal to 1, and I can make C, I guess, would have to become equal to 1 for this to be the same as what we had today. But, you could try what, changing different values does to the curve, and I feel like you can learn a lot quickly if you use these sliders. So what I think I'm going to do is I'm going to try and finish the baseball problem on GeoGebra here, and so I'm going to do a little editing. So let me go back to this curve, the helix, and I'll turn this one off. And so I want to edit this. And so I'm going to say that A is equal to the curve, and I'll type in what we had in class. So rather than cosine t, sine t, t, we have 30t, comma, 2.5 t squared, right arrow to get off of that, plus 30t, comma, and then, let's see, negative 16t squared, plus 80t, plus 3. And then t is my parameter, and I want it to range from 0 to what? Well, not 2 pi necessarily, although actually it might get good results. I'm trying to figure out how long do I want to see this curve going, and I'm going to guess that a baseball wouldn't hang in the air more than, say, 6 seconds. So that ought to be enough to fix things up. So I'll press enter and see if I can get a picture here. Of course, one interesting thing is it seems to me that my window is far too small because it's only going from 0 to 10. And if you think about that, we were talking about feet. I mean, a baseball field might be 400 feet in width. So I'm going to need to change the dimensions too. And you can see the ball taking off, but if I want to see how long until this thing lands, I need to change the dimensions of my window. So let me figure out how to do that, and then I'll show you here in a second. Okay, I may have something that works here. If I click on the menu, I can say that I want to open this with the GeoGebra app. And then you have some nice features. Of course, this is useful for geometry. I have some nice features here that I don't have otherwise. And so I'm going to try and do that. And so you'll notice when I click on it, there's the arrow tool, which I have now, but there are a lot of other tools which can allow you to take a look at what we have here. It looks to me like I'm going to have to re-enter my curve again. For some reason it didn't save and then open. Here, let me go back here. let me save it, and then try opening with the app. I don't see a save. Let me try this. Open with the app. Because for some reason, it's going back to the Helix. And I'm not quite sure why. I don't want it to go to the Helix, but it seems that that's what it's going back to. So, I guess what I need to do is I need to somehow save my changes. Yeah. So you don't get those buttons here. I made my change, but it didn't seem to save, which is unfortunate. I mean, I even changed the title. You can edit that. So I did this all under edit. Maybe I should copy this so that I don't have to type it all again. Let's see if we can do a Control C and Control V kind of situation. Okay, and let's highlight what I just had. And now, what I wanted to show you guys was, there's all these different options up here, but the one that I found was the very last one, this kind of funny looking rotation, rotate 3D graphics, move, etc. You can zoom out. And so if I select that and then start clicking on the object enough, you can zoom out until here we're at seeing 150 or 250 feet. And you can even see when it's going to break the surface of the plane again right there. So that's really kind of nice. Looks to me like you might be able to do some different T's also. So I'll tell you what I'm going to do. I'm going to copy this function into B, and then I'll still have T go from 0 to end time rather than from 0 to 6 like we did last time. And so if I copy this in here, there's B, and we will graph B rather than A. Of course, it's the same curve, so you can't see any difference, except for the fact that now I can change my end time. And so when I'm at 3 seconds, it's still up in the air, or the highest point is somewhere around 1.75 seconds, 1.8. You guys are going to work that out tonight when you do problem 50. And it looks to me like splashdown happens right around there, like around just a little more than 5 seconds is when it's going to hit the ground. So again, I think these are some nice things you can do with GeoGebra. I'll try and save some of this for you, and I have a feeling that, at least for the time being, this may be what we play with when we're working on Chapter 13 here in the Calc 3 class. Nice work today, and good luck with your homework. I'll see you on Wednesday.